Welcome, everybody. Before you all go into your postprandial sleepy time, I want to welcome you all to our spring 2018 MSREI conference and dinner conference. And this is a time that we all have a few moments out of our crazy days to spend time together and stay connected, and friendship and collegiality and learning more on so many levels that only comes when we actually meet with each other face to face and not texting or FaceTiming or remotely connecting in one way or another. So I'm so glad you all could make it, and we want to make this evening so worth your while. I wanted to start tonight with a little bit a story, a personal journey story that I've experienced that will lead into introducing our guest speaker. And this happened a long time ago, not in a place that far away in Baltimore, where you can raise your hands if, well, actually don't, but this is a story that starts with Georgiana Jones. And Georgiana and Howard Jones have had several careers. The first career was at Johns Hopkins, and they had a mandatory retirement at 65. And then their second career started through the Hopkins connection to go down to Norfolk and to enter the world and help us enter the world of IVF. So when I was a resident back in the mid-'80s, they invited Howard and Georgiana back to Hopkins, and I was an intern then, and we were having a conference in Dr. Wallach's conference room as the chairman, and Georgiana Jones sat down next to me, and I felt like I'm sitting next to living history, because Georgiana started the first infertility clinic in the United States. It was at Johns Hopkins in 1939. And although Howard Jones gets the major memory spotlight, either from Henrietta Lacks, the HeLa cells, he was the surgeon, GYN surgeon, collecting that cervical cancer that changed a lot of what we do, but also challenges how we get informed consent. They had a second career, but I was able to sit next to Georgiana. And I was just learning new stuff in GYN and running through the infertility rotation. And I realized while I was sitting there, this is the person that really got things going for endometrial biopsies. And she collaborated with Dr. Noyes in 1951 to begin to describe the day-to-day changes in the endometrium that you'd see under the microscope. And then they wanted to correlate this to a woman's menstrual cycle versus the tissue histologically under the microscope. And when it's more than 2 days disparity of the microscopic view behind what it should be by the calendar view, we consider that out of phase. And that was how we defined luteal phase deficiency or luteal phase defect. So now she's there, I'm a little nervous, she sat down next to me, and she's very maternal. She just looked at my name tag, or ID tag, and she said, "Hi, Michael, do you like to be called Michael or Mike?" And I said, "Mike's fine," history. Giant in our field. And she just started asking me a few questions about family, other things like this. And then I got up the courage to ask her a question. I said, Dr. Jones, she said, "Call me Georgie." I said, "Dr. Jones, this whole thing about endometrial biopsies is something that's sacrosanct. This is what we do. But I have a question." And she said, "What's that?" I said, "How did you know more than 2 days out of phase was abnormal?" And she paused, and then she had this huge belly laugh. And she said, "I had to make my best guess." And then I looked at her, it was like reflex, I said, "But how do you know you're right?" And this is the linchpin. This was a moment that I'll never forget, and something that I want to pass on to you. She said, "That's for your generation to figure out." And I still get goosebumps when I share this experience, because her point to me was challenge settled ideas. We don't always know why we do it, and we need to find our why. And she said it with such humility. Of just an eagerness to do something new, to learn something new, that she wasn't in love with her theory. It was meant to be revised. And I'll never forget that moment. And I wanted to share that with you tonight because I think it's relevant. Because our speaker tonight, Gary Hutton, he's also been asking why and what's new, where are we going, what's the next step. And I guess like a football receiver, you go to where you think the ball's going to wind up. You don't chase the ball from the passer to get there. And Gary's history would be, he'd be a really good receiver in that way. Just a little bit, as I have some stuff written down for background for Gary. He got his, should I say your BS or bachelor in science?
Say again?
BS or?
BS.
Okay. He got his BS when he was, I think the battery's running low. Anyway, can you hear me okay? So he got his BS at age 10, then he got his bachelor's degree at 22, right? Okay. But also, this is at James Madison, and he got his PhD at University of Kent in Canterbury, UK. And his thesis was titled, Facilitating the Widespread Use of PGD and PGS Through Best Practice in Novel Technology Development. I think it's very relevant to what Georgiana Jones was teaching me to think about. And he's had, well, on his third decade, when I hit my 50s, my then 10-year-old said, I've entered my 6th decade of life, congratulations. So I can say third decade for you. And, but has been involved in business development, different aspects of really bringing technology to the marketplace in a meaningful and useful way. I could go on more into the specifics he's done in the various areas of PGD, PGS. He's trained many folks who are really thought leaders and helpful today at every station in our field. So I think that these are all key things that we're going to learn a lot tonight. There was one other thing before we start I wanted to share with you. It was a quote. I don't know how many have to travel long distances to get to work or do other things, so you may have audible books or you listen to, or you do your Kindle or read certain things. But I recently listened to a book by Siddhartha Mukherjee, who's written several Pulitzer Prize winning books. The most recent one is on the gene. And there's one thing I wanted to quote. It's a little bit long here, but then we'll move on with Gary really educating us. And from that book, here's the passage. The capacity to manipulate genes represented nothing short of a transformation in genetics. It is the impulse of science to try to understand nature, and it is the impulse of technology to try to manipulate it. Recombinant DNA has pushed genetics from the realm of science to the realm of technology. Genes were not just the subjects of study, they are the instruments of study now. We have transformed our perception of science from thinking about genes to thinking in terms of genes. Recommendation, so this is just such a key point that now we are really using tools, genes as the tools and not as the subject. And into microarrays, into next gen, all sorts of stuff. And with that, I yield the podium to Gary Hutton. Gary.
I don't know that I've been introduced so eloquently ever before. I very much appreciate that. I have my own Dr. Jones and Dr. Jones story, although it's not Georgiana, it's Howard. I gave a lecture at EVMS and Jones Institute some number of years ago, and I was a bit younger then. And I was very worried about Howard Jones coming to the lecture because he's a pretty smart guy, and I don't know that I could hold up against him. And the first person that gets there is Howard Jones, in his wheelchair, listening to a book on tape, because he wastes zero time in his day. He's always doing something, even between lectures or meetings or whatever. In his wheelchair, he has a book on tape playing at all times. And it was just, for me, it was a lesson learned in finding ways to make your day useful. So today, we're going to talk about endometrial receptivity. And I will admit, this is not my first field of study. As Mike pointed out, I'm a PhD, PGS guy. So if this were that talk, I'd feel pretty confident. That it's on endometrium and some of the new things that we're doing in looking at genes in endometrium, I'm going to do my best to educate and hopefully answer some questions. To start out, I have to, of course, I do work for a company, so I do have to do some disclosures. I do work for iGenomics, the company that makes and sells this test. I am also on the medical advisory board for Cryos International. So those are my disclosures. So I aim whenever I give a lecture to not make it to be a commercial for me or for my company, but I just do need to point that out. So the agenda for today then is we're going to talk about endometrial receptivity, at least the way I see endometrial receptivity in perhaps my simplified way. We're going to talk about the ERA test in particular. We're going to talk about a couple of new things because in the end, what's new is always more interesting than what we do today. We're going to talk about the concept just in one slide of putting PGTA and endometrial receptivity together. You know, I told Alyssa that the name of this talk was the other part of the window, right? What are you not seeing if some of the window isn't there, you can't see through it. And then last, I'm going to talk a little bit about quality control because in the end, as a laboratory partner, it's our job to help you understand your clinical practice and how we can help you practice better and how you can help us do better lab tests and get better outcomes because in the end, we're all here for our patients, right? That's why we're here and what we're after. So again, I mentioned, you know, this is sort of a simplified concept. But as a guy who spent his entire life, my 30 years, thanks for pointing that out to everybody that I'm just getting old, is really all about, you know, embryos either implant or they don't implant. It's a pretty simplified way to think of it, but that's how I've always thought about it. As a guy who spent my career basically testing embryos, there's only two options, right? There's the green option of it implants and the red option of it doesn't. I think, you know, you can make this green box bigger or smaller depending on maybe when you started in the field. When I started in the field, the green box was quite small. It was maybe 25%, you know, 25% of it, and the rest of it was red. And we've made great strides in the 30 years I've been doing this to have this green box be the majority of embryos, right? It's somewhere between 50 and 65%, let's say. But this is maybe a little bit simplified way to look at it. You could also look at it then as, which is, I think, more interesting, is not all good embryos implant. So again, you've got the same green box of euploid embryos that implant and that same red box of embryos that don't implant. But I think really the future of the field, the thing for the next generation, perhaps not me and my generation, but the next generation, you people, you young people here, is this gray box in the middle. To me, this is the most interesting part of IVF in the future. Right? These are all the things that we can do to whittle away at why do good embryos not implant? Why do good embryos not make live-born children? Right? Some of that is going to be more genetic testing, maybe better genetic tests of embryos. Some of that might be time-lapse or different omics. And certainly ERA, what we're going to talk about today, fits inside this green box. Right? The idea that you can have good embryos and they still might not implant because you're not transferring them at the right time. That's what the idea behind ERA is, and that's what we're going to talk about. But for me, this gray box is the future. This is the box that Mike talked about. This is for the next generation to figure out all the things in this box that can whittle away at all these good embryos that don't implant. And if we can get 3% or 4% or 5% or 10% with every new thing we can do, then ultimately most patients are going to come home with a baby, which would be our goal ultimately. So I look at this as not all euploid embryos implant. We're not going to have an argument today about whether PGTA or PGS works or not. That's not what I was invited to do. I'm happy to do that. I'm happy to do that argument someday with somebody if you'd like to. But today it's about not all good embryos implant. And so I have to admit, I like to have pictures, not a whole lot of words on my slides. And I have to admit, I stole this idea from somebody else that did this. But this sort of, for me, sums up ERA in a one picture, right? Trains run on time in theory. Anybody that takes a train anywhere knows if you don't turn up on the time the train's going to be there, it's going to be gone. And so that's the same thing with endometrial receptivity. If the embryo gets there either too early or too late, then it's not going to implant. That's pretty clear, right? And so this is a very simple way to look at the concept of how ERA works. So ERA started out as endometrial receptivity array because it was based on an actual microarray. It had 238 genes. So let's be clear right here and right now, this test is a molecular genetic test. to look at endometrial receptivity through gene signatures. Which genes are turned on and which genes are turned off at certain times during endometrial development that belie whether an embryo has a good chance of implanting or a bad chance or less chance of implanting. So like everything else, Mike mentioned this as well, and I'll tell a little anecdote about one of my favorite people in the field, Jacques Cohen, who tells me there's two things about geneticists everyone has to understand. One is nobody cares as much about genetics as I do, right? I start talking and your eyes roll up at the back of your heads in about 30 seconds. That's the general time I get, right? That's number one. And number two, this is what drove Jacques nuts when I worked for Jacques, is geneticists love new toys. If a new sequencer comes out and it's got a blue button instead of a green button, we just have to have it, right? I mean, you guys know. You got to have it. It's new. An embryologist will keep the same microscope for 40 years, and it'll have baling wire and bubble gum, and they will not give up that microscope for anything. Geneticists, I will throw out everything and get a new machine tomorrow. So, of course, we had to move to next gen. Now, I'm kidding. Next gen does offer a whole lot of superiority over an array. It's a lot more, if nothing else, it's a lot more adaptive to things you want to do. So we're now using next gen. We did lose 2 genes along the way, so now this next gen platform looks at 236 genes, right? There's a website you can go look at all the genes if you want to have a look. We can do that. I'm not going to list all the genes for you today, but there is a list. And this is the concept of how this thing works, right? This is what's called a hierarchical cluster of genes and gene regulation. So if you're a geneticist, you know that genes regulate protein, right? And when a gene turns itself on or gets turned on, it will produce more protein, or if it gets turned off, it will produce less protein. And you can use that to look at signatures within the uterus that tell you whether the uterus is proliferative, pre-receptive, receptive, or post-receptive. And that's essentially what this does. It looks at which genes are turned on and off at certain time periods, knowing what happened clinically from those kinds of patients. Now, I'll pause here and also point out one other thing that one has to understand about this test. We do not believe that the day you do a transfer, the embryo comes out of the end of the catheter and goes right into the uterine wall. That's not how this works. The signature we see tells us that the time to transfer is now, to give you the best chance of that embryo implanting at the time when it's going to implant. The embryo doesn't zip out and go right into the endometrium. We know that. We do get asked that question all the time. So it's about the signature at the time of transfer, and that's really critical to understand. So ultimately then you get some number of potential answers to which genes are turned on and off, and it's an algorithm, right? It's how it works. And so the sample will fall in a number of places. It can fall in proliferative, it can fall in pre-receptive, it can fall in receptive, post-receptive, or really post-receptive, right? It's sort of a horseshoe-shaped option where the sample falls. So each of these dots that's here in all the colors are the thousands of samples we've already run and we know the outcome from. Then you put an unknown sample. When it falls within that algorithm, you can then predict what's most likely to happen for that sample. And that's how any algorithm works. No matter what you're doing with an algorithm, that's how an algorithm works. You take data, understand what happened, and then look at an unknown compared to all your knowns and say what's most likely this sample when compared to 20, 30, 40,000 other samples of the same. So the test today is based, the algorithm today is based on 24,500 patients. And for all you people, everybody here that's a physician that sits in front of patients, these are numbers that you're really going to want to pay attention to. 24,500 patients, and I'm going to have to put my glasses on to get the numbers right. Now remember, we're a reference laboratory. I don't tell anybody how to do my test, right? We have a test, we sell it. And every doctor does it slightly differently, okay? So these are just the 24,500 samples we've received in our lab. The vast majority, we'll talk about who uses this test or how you use the test. We'll talk about that in a moment, but these are just the samples we've received. The number you really need to know is about 35% of those patients so far have been non-receptive. So in other words, you're transferring the embryo at the wrong time in 35% of those patients. The vast majority of these patients have failed IVF before. These are not first-come IVF patients that have never done an IVF cycle before. Most of these patients have failed a few transfers, and today in the US, mostly a few transfers of euploid embryo. Now the other thing to know is once you get a non-receptive, the vast majority of those patients, about 87% of them so far in our data, are going to be pre-receptive. And that's really good, because it just means you need to give them more progesterone. It's a quite easy fix. So most patients that when you get to this test, most patients are upset at most tests when they fall out of the normal. Patients that get the ERA test are upset when they fall into receptive, right? They'd rather be non-receptive because to them then it's an answer. I haven't gotten pregnant before, maybe this is why, right? This becomes then personalized medicine. It's personalized embryo transfer timing. So most patients are pre-receptive, meaning you simply need to give them more progesterone. And we've hammered on this algorithm to get to the point now where we can tell you in about 90% of patients whether they need 12 hours more or 24 hours more or 12 or 24 hours less if they're post-receptive. And we'll talk about how that works in a second. The last thing to really know about this test is it's fairly pan-ethnic, we're pretty sure. So this is, these results, these 24,500 patients, samples, have come from 54 countries and over 600 IVF centers around the world. So you don't need to necessarily worry about this patient is this ethnicity, does it work for that ethnicity? The answer is we're pretty sure it works for everybody. Okay? So that's a couple things about the data that we have today so far. So then let's talk about how this test theoretically works. So if a patient comes back receptive, that means that our gene signature profile suggests that you're transferring at the right time. That's P plus this 5 days of progesterone, about 120 hours. They come back receptive, that's the time. It's not that you're transferring at the wrong time, it's something else in that patient. Again, that's the one that makes most patients upset. They can be pre-receptive, again, meaning that the uterine lining is not ready today, it's going to be ready down the road. They need more progesterone. Or it can be post-receptive, meaning the uterine lining, the endometrium was receptive previously, and they need less progesterone before you do the transfer. So again, it's all about personalized embryo transfer timing. And again, because I'm a pretty simplistic guy and I like cartoons, theoretically, if you're transferring embryos in pre-receptive uterus or a post-receptive uterus, the chances of getting pregnant are quite slim. Now, it's not going to say it can't happen, but it happens more likely if it's in a receptive uterus, right? That's the idea, again, behind the test. So in practical terms, then, this has to be done on freeze-all cycles. This cannot be done on a fresh cycle. So just understand, all frozen, which isn't a big deal most places in the United States because most people do all frozen anyway. So here you get a patient ready for an FET. However, instead of transferring the embryo, you do an endometrial biopsy. As Mike mentioned, most people know how to do an endometrial biopsy. You do that biopsy, you send that test off. And in this case, we did 120 hours. The patient is clearly in the pre-receptive phase. She's not receptive today. She's going to be receptive down the road. You get the result back. The result says she's pre-receptive, 12 hours. Give her 12 hours extra progesterone, which usually means to start the progesterone half a day early. You can also do a transfer half a day late, but most embryologists and nurses and doctors don't want to be doing transfers at 8, 9, 10, and 11 o'clock at night. So just start progesterone half a day early, right? So here then you give her 132 hours of progesterone. She falls right in the middle of the window of implantation. You've done a personalized embryo transfer, and hopefully this patient then comes home pregnant now. That's as simplistic as I can make it, that's how the test works. So a couple of the things to note about this test, the questions that I get asked all the time. The first one is, well, how do I know it's better, right? There's a classic test, obviously, of doing an endometrial biopsy, sectioning that, and having a pathologist look at the test. So one of the first things we did was look at pathology, looking at proliferative, pre-receptive, receptive, and post-receptive versus the ERA test. And I'm not going to belabor the point, but in every category, the ERA test, because it's molecular genetics, it's not someone looking down a microscope and telling you what they think. It's a molecular signature. It's a molecular genetic signature of what we think the uterus is. So we always outperformed the pathologist when we did that comparison. The other one that you'll hear a lot of is this concept of endometrial scratching. The idea that you do a biopsy to create some sort of an inflammation, some sort of a reaction locally at the uterus that somehow belies a better chance of getting pregnant. Right? Now, there are plenty of people, plenty of smart people that still believe in this. And a lot of people do endometrial biopsy and ERA because they think it's not going to hurt to do the scratch as well. Okay? But in this study, what we looked at was some number of patients that had an ERA at some point in their treatment. And then in month 1, there were 91 patients that did transfer after 1 month after the biopsy. Right? And then so on. 2 months, there was 87 patients. At 3 months, there was 47. And you can count down and see what it was. So these are biopsy today, and then did you have the transfer 1 month, 2 months, 3 months, 4 months, 5 months, or 6 months after the transfer? And the pregnancy rate and the implantation rate that came from that. And what you can see very clearly from the chart then is that the scratch isn't what's causing implantation 6 months later. I can't imagine that a localized reaction to a scratch to an endometrium that's been shed 6 times is going to still be producing an effect, right? So for us, this is the definitive proof that the scratch isn't what's causing implantation, it's the actual test and personalized embryo transfer, okay? The other thing that you really have to understand, and I think it's one of the really strengths of this test, is that ERA results remain constant over years of time. So you don't need to do this test over and over and over again on patients. You can do this test once. So this is a look at a number of patients. So the first one I'm going to show you, that patient, that's 4 years, 3 months apart. And you can see how closely they cluster 4 years, 3 months apart. As long as you use the same endometrial development and the same timing for the biopsy, you'll get the same results. The only thing that changes that is BMI. If a patient massively gains or massively loses BMI between those 2 tests, you're likely to get a different answer. The other way you'll get a different answer is obviously if you use a different regimen to get the patient prepared. If you use the natural cycle once and a stimulated or a HRT cycle the next time, or if you use this HRT cycle this time and a different HRT cycle that time, you're not going to get the same results, right? But if you use the same preparation in the same patient, as long as BMI hasn't changed drastically, you should get the same result, which means you can do an ERA on a patient one time, and you shouldn't need to repeat that ERA ever again on that patient, hopefully, which I think is an advantage of the test clinically. So we're going to publish this paper later this year that we finished collecting the data. This is all I have today to show you. Unfortunately, it's almost 2 years old now. But this was the interim look at a study that we're doing. It's a randomized controlled trial. It's a 3-armed clinical trial. So FET in Europe is fresh embryo transfer. So I'm sorry, I forgot to go change this slide. It's not FET like it is here, but in Europe, FET means fresh. DET means delayed or frozen. And then PET means personalized embryo transfer after ERA. Now, this is an interesting study because this was not the typical patient population that most clinicians in the world use for ERA. This was all comers to the IVF center. This was patients that had never done an IVF cycle before, never failed. And here's all the inclusion and exclusion criteria. Be clear that aneuploidy screening is not an inclusion or exclusion criteria. So some of these embryos are euploid and some of these embryos are unknown, for sure. This is how the patients broke down in the interim look. It's not a massive study, but it's not too bad. And like I said, we finished collecting. We haven't finished getting all the data. The live birth is the outcome. So we have to wait till we finish collecting patients, enrolling patients, and then wait 10 months for all the babies to be born. And that's what's taking so long to get this out. But interestingly, if you just look at pregnancy rate per embryo transfer, in the frozen group, not bad, 61.7%. Again, these are not patients that have been failing IVF, so that's not unrealistic. In the delayed or frozen embryo transfer is 60.8. In the personalized embryo transfer, it's 85.7. That's a very statistically significant difference in implantation rate. Now, if you dig into this data, I don't have the slide, but if you dig into the data, one of the things that came out of this that's quite interesting is the error bars on when the embryo transfer got done in the fresh and frozen are way bigger than the error bars on people that did personalized embryo transfer. So the ERA made them, for whatever reason, be very strict about transferring at the right time. The rest of them, they let the clinical day get in their way. I like to transfer at 10, 17 things went wrong today, I transferred at 2. Right? So there's massive error bars there. So probably the implantation rate difference isn't probably as large as this is showing. We'll see when we get the full data. But you can have a look at that if you want. So the conclusions from the trial, these are the presented conclusions at ASRM, were that personalized embryo transfer guided by ERA is associated with significant improvement in reproductive outcome in terms of pregnancy rate, and a trend towards increase in implantation and ongoing pregnancy rate versus fresh or frozen embryo transfer. The other idea here was that in light of this data, this may become a screening test down the road where you just screen every patient. If the price is right and the preparation is right and you're freezing embryos anyway, the idea might become, why not make sure you're transferring at the right time in all patients? And we'll talk about that in a minute. This is a very recent paper that just came out from a group that's completely independent of us. This is the group at Olive Fertility up in Vancouver. And they looked at patients that had failed some number of euploid transfers and then did one more transfer with ERA or one more transfer without ERA. It's a small study. They did not reach significance, but there's a definite trend in ERA gives better outcomes when it comes to implantation rate and pregnancy rate. This is a really nice study. You can certainly have a look at this. Then the last thing, again, I'm a scientist by training, so I believe in not just telling you something's great, but showing you data. Right? I'm going to put my glasses back on for this next one. I just got this slide today, so you have to forgive me if there's any spelling errors. I did this on the plane on the way here, so again, forgive me. But I asked the team in Spain that developed this test, right? We're a Spanish-based company in the end. We're making a really big push to get clinical data from real cases, right? I showed you 24,500 samples we've run, and sadly, we've only collected about 400 outcomes from those 24,500 patients, but we're doing the best we can. Unfortunately, IVF centers don't like to share their data back with us. I wish they did, but they don't. We're working on that. So this is the sum total of all the clinical data from patients that have been sent to us as a test that we've been able to get answer back from what happened when you did a transfer for those patients, right? And so they're the typical things, number of embryo transfers, implantation rate, pregnancy rate, biochemicals, miscarriages, ectopics, ongoing pregnancy, and then ongoing pregnancy per transfer. So if you look at personalized embryo transfer after ERA was receptive, so in other words, do the transfer at the same time because that patient was receptive, you can see these are pretty respectable numbers, right? It's not huge, it's 194 patients, but in the end, those are very respectable numbers. And again, remember, these are not all euploid embryos, right? This is data from all over the world. This is whatever embryos were transferred. If you look at personalized embryo transfer after the window of implantation was corrected, so in other words, they had transferred embryos, didn't get pregnant, did ERA, moved the window of implantation, or the time of transfer based on the result, it's 289 patients. Again, very, very respectable numbers. What this shows me in a quick look is that it's as good or better than, if you move the window, you're clearly getting that person into the window of implant, the receptive area, right? So the first column is patients that were receptive. The second column is patients that weren't receptive, but we moved the transfer to meet receptivity and got the same exact results. So to me, that's really powerful data. Again, completely independent. These are just patients that have been sent to us that we've been followed up. And so we're pushing to continue to get more and more of this data. So if anybody here uses ERA and you want to share your data with us, we'd love to have it back. So if you do it, you should have received a chart. Please fill out that chart for us. We'd love to have it. So if you take all those embryos transferred together, then you see the numbers here. And again, the idea here was to show you some just completely independent data that shows how ERA can work clinically in a certain patient population. So then let's talk about clinically how to use the test, right? I showed you how the test works. I showed you how to do the test. Today, the vast majority of people that do this test perform this test on patients that have failed 1 or 2 euploid transfers. And again, we work in America. Let's be realistic. Not everybody here maybe, but a lot of practices do PGTA on almost everybody. And so it's a lot of euploid embryos. So most practices use it. Usually it's 1 or 2 failed embryo transfers with good quality embryos. A lot of those are euploid embryos. We're seeing more and more people that use this in donor eggs after 1 failed donor cycle. Because again, let's be realistic, most patients with donor egg get pregnant on 1 transfer, right? 70% plus. So a lot of doctors are starting to use this test on donor egg recipients if they failed 1 transfer. So future patient populations, as we look down the road, all patients that opt for PGTA, maybe, why not? You're doing genetic screening on your embryos. Why wouldn't you genetically screen your uterus as well, right? Again, if the price is right and you're going to freeze the embryos anyway, perhaps that's a place you might think that this test would go. All patients as a screening test. I mentioned that data from Dr. Simone and his group. There's a couple of docs here in the US that started with 2 failed transfers, then went to 1. Now they offer it as a screening test to every patient that walks through the door. And they're finding not every patient says, yes, I want to do that as a start, but they're finding really good success at pulling those people out that are going to have a transfer at the wrong time and transferring them at the right time. And there's some really compelling data that's going to come out soon from 2 clinics that are using this test as a screening test. It's really nice to see. So if you look at that data, if you dig down in when that paper's done, it turns out that all comers that came to the IVF center, About 1 in 6, 1 in 7 of them had an implantation window that was not where it should have been after 5 days of progesterone. That's about 15 to 16% of your patients are coming in, they're not receptive at the time you think they're receptive. So again, you can see how this might become a screening test. Now the other thing we like to do, this is a molecular genetic test, okay? It's not looking down the microscope, so the more tissue, the better, is not how this works for us, right? In the old days, you have to section, send a bunch of tissue, that's great. Here, that's not great. So I have a picture here of what the perfect biopsy looks like. The reason is this is an RNA-based test. To look at gene regulation, you need RNA. Anybody that's ever worked with RNA knows RNA is really hard to work with. It's really, really labile. It's hard to work with. So that fluid that you're putting that tissue into is actually an RNA stabilization fluid. It's not just PBS with something in it like we do for PGTA. It really is doing something. When I ask you to please shake that tube for 10 seconds, I really mean shake that tube for 10 seconds. When I say put it in the fridge for 4 hours, I really mean put it in the fridge for 4 hours. That's actually capturing RNA. The reason we don't want too much tissue, if you put too much tissue in there, there's not enough fluid to capture all the RNA. The RNA that doesn't get captured starts breaking down, and that breaks down all the other RNA, and you get no result. So not enough tissue is a bad thing. Too much tissue is a bad thing. The sweet spot is right there on the picture in front of you. We actually have a card we can give you that says, this is what the perfect biopsy looks like. It shouldn't be too bloody. It shouldn't have betadine or anything else in it. And it should be a nice-sized endometrial biopsy sample. And most doctors, this is what we get. We do get some outliers occasionally, but that's what a perfect biopsy looks like. Now I want to finish up with 2 things that are new. Because again, I think that stuff I just told you is pretty new, but we like new stuff. I'm a geneticist. We love new things. So I'm going to talk about 2 other things that we're doing in the clinic or in our lab. They have to have fancy names because in the end, we are a company. They're called Emma and Alice. Emma is looking at the microbiome of the uterus. Alice is looking at chronic endometritis, right, which is a really hard thing to diagnose. So if you're a doctor and you're worried about chronic endometritis, it's really hard to diagnose chronic endometritis. So we're going to talk a little bit about those. And again, I will admit, this is getting a little bit far afield from where my world has been for 30 years. So forgive me if I skip anything. If you don't understand it, we'll try to get to it. That's the paper that started. Emma looks at the microbiome in the uterus. So in the paper, you have to read the whole thing. It does prove that there's a different microbiome in the uterus than in the vagina. So you're not just picking up microbiomes as you go through the vagina. They're different, and they are separate. And so it's quite interesting, and I'm going to show you the flow chart that I think is the most interesting way to look at this data, because that's a little hard to read. This is a bit busy, but if you look at the other thing I should say, it's a pilot study. This is 41 patients, okay? So while I'm going to tell you it's really cool and it's going to be really compelling, exciting data, it's just 41 patients. We have to prove this in a much larger study, clearly, right? So if you look at those 41 patients, and again, I need my glasses here, and you take the ones that were receptive, either they were receptive on the biopsy or you've moved the window of implantation, and every embryo that was transferred here is a euploid embryo, okay? So you're looking at, if you look in the receptive group, you're looking at receptive by ERA and euploid by PGTA. If you go to the very top, lactobacillus dominant, the LD group, that's a good microbiome, is lactobacillus dominant, okay? If you look at that, then you've got a pregnancy of 12 out of 17 of those patients got pregnant, 5 out of 17 didn't get pregnant. That's 70.6 and 29.4. That's a pretty good rate. If you then look at ongoing pregnancies, you look at the loss rate there, it's 58.8%. Okay, so very, very low miscarriage rate, about 10%, which you'd expect from euploid embryos. If you look then at the non-lactobacillus dominant group, you'll see that the pregnancy rate was only 33%. So 33 in a non-lactobacillus dominant group, same ERA positive, PGTA positive, normal. The non-pregnant rate is obviously the opposite. If you then look at ongoing, look at the miscarriages there, you'll see the miscarriage rate was 60%. 60%. So that's a much lower pregnancy rate and a much higher miscarriage rate in a non-lactobacillus dominant uterus. So what this tells us then, which we're really excited about, is another part of that gray box might not just be euploid embryos or endometrial receptive uterus, but also microbiome. And it turns out there's something you can do about the microbiome as well. So we don't sell it. I wish we did, wish we owned it. There's actually a tampon that has lactobacillus dried lactobacillus in the top of the tampon. When it gets wet, the lactobacillus goes up through the cervix and gets into the uterus and can theoretically fix a non-lactobacillus dominant uterine lining, uterine microbiome. So we're working on all those things and looking at whether that tampon really works or not. So again, more of that gray box, theoretically, right? So you will be able to order this test clinically soon. It'll be on the same exact sample that you do for endometrial biopsy. You'll be able to tick a box that says, I want EMA, and you'll get the EMA test in addition to endometrial receptivity if you believe in microbiome and if we can prove this. And I'll talk about a study we're doing right now to look at that. And again, it's on the same exact biopsy sample, so nothing additional the patient needs to do. This can also be done outside of an IVF cycle. Obviously, the microbiome, it changes, it goes up and down, but it can be done as long as it's done at a certain timing of the cycle each month. It can be done also outside of FETs and everything else. ALICE is chronic endometritis. Again, I think anybody that's a physician here will tell you that chronic endometritis is really, really hard to diagnose in a patient. And it, again, is probably more of the gray box, right? You're transferring embryos into a uterine atmosphere that isn't ideal. So this, again, is one of the early studies. It looks at physical ways to look at chronic endometritis, hysteroscopy, HSY, and culture, right? And if you look at these things, so histology, hysteroscopy, and microbial culture, you'll see that very few times does each of those three tests call the sample the same way, right? So there's not a whole lot of concordance between various ways to look at this problem. So again, you take molecular genetics and you compare concordant samples between all three of the ways to call chronic endometritis versus the molecular test, and we got much better concordance looking at those things. So we're pretty confident that a molecular look at chronic endometritis is going to be better than histology or culture or hysteroscopy. Now the other thing is, again, because it's a molecular test, you're getting a signature of not only is there chronic infection, but you're going to know which bacteria it is that's infecting, and so you can personalize then the antibiotic treatment based on the microbe that's present, which again is really exciting. Very, very small pilot initial study, so again, can't get too excited about it, but very, very exciting stuff. Again, same idea, can be done during the same biopsy, just tick the box. I want ALICE as well. And again, not to make this too much of a commercial, I'll skip through that. Again, we very much believe in doing clinical trials. And so this is a very large prospective study looking at the endometrial microbiome. So it's looking at non-invasive ERA compared to invasive ERA, and looking at microbiome and chronic endometritis, and comparing the two different groups, right? One group done classically and one group done with these other two tests. See if these other two tests really in a large study can follow up those pilot studies that we did. Do the data hold? So I won't read this whole slide to you, but this is sort of how it's broken down. One arm is just ERA and transfer. The other arm is look at all three of those, and then go back and do transfers and see if that gives you some advantage. Here's the groups that are in it. It's around the world. You'll notice there's some really nice big practices in there. But again, the idea was to do it all over the world. Now, the last thing I want to talk about, which is something that's near and dear to my heart as a guy who's worked in a lab for a long time, is quality control. Right? It's something I think that it's really important to understand who you send your samples to, and do they know what they're doing, and are your results correct, and are they giving you good reports, and do they take good care of you, right? So we've begun doing this. If you'll share your clinical data with us, we can produce a report for you that can compare your outcomes versus the rest of the United States, the whole world, the state you live in, the area. We can compare it really to anything, because we're really lucky. We have a massive lab information system that every single sample that comes into my laboratory anywhere in the world goes into this system. And I have a dashboard. I can pull up anybody's IVF practice and compare aneuploidy rates, mosaicism rates, receptivity rates, anything that you do, I can look at. If you tell me which embryologist did the biopsy, I can tell you what their rates look like compared to other embryologists. If you want to know, I can tell you how Tech A in lab New Jersey reports results compared to Tech B in LA. We can do those comparisons internally as well. So here for ERA, what we can show you is what your results are receptive versus non-receptive is versus global ERA data, again, the US or regional, we can do it against anybody. So you can see how your practice is compared to another. And I'll give you a quick anecdote of why this is important. Had a very big practice in the US come to us and they said, we feel like we get a lot of non-receptives. We want to see how we compare to somebody else. Can you do this for us? I said, yeah, great. We're just rolling this out. We're going to try it. They had something like 72% of their patients were non-receptive. If you compare them, I just told you it's about 35% are non-receptive in the world of all the data we have. So we went back then and looked at all the things that could be the reason. Is it a doctor? Is it this is a big practice? There's lots of different doctors in lots of different places. Is it the doctors? Is it something you're doing? Turns out it was the number of hours of progesterone. So they use, they're big believers in progesterone and oil. They tell their patients, you need to start progesterone today. They never told them what time today. They just said you need to start it, today is day 0. So most of their patients were waiting until their partner got home to give them that really hard shot. And so they weren't starting progesterone until 8, 9, 10, 11 o'clock at night. So by the time they got to what was day 5, it was only day 4.5. Right? They were only getting on average about 102 hours of progesterone, not 120. So they changed clinical practice. They got everybody together. They started mandating, you have to start progesterone at this time, and we do all of our biopsies at this time. Their non-receptive rate's gone back down to right where it should be. It's at 32% right now. So it shows how quality control can help you manage your clinical practice. They might have said, I don't care, but they felt like having all those non-receptives, it was getting in the way of patients that were probably receptive were still doing transfers at extra time and all that. So it's a way that this QA/QC can really help guide your clinical data. We can also look at the number of times you have to do a second biopsy because you got you didn't get an answer. Either we didn't give you a window or you got an invalid RNA, that kind of thing. And then if you give us the pregnancy rates, we can compare your pregnancy rates based on implantation pregnancy and ongoing pregnancy from personalized embryo transfers against anybody else in the world or the US or whatever you want to do. And again, it's a way that you can very much think about how we can work together to change your clinical practice. Right? I think that's really, really important to understand is that this is a partnership. It's not just you, it's not just us. We're all working together. I also, again, I'm a PGTA or PGS guy. I have to talk about PGTA. It's just one slide. But we have this idea called synchrony, looking at both genetic testing of embryos and genetic testing of the endometrium to make sure that those things are matching up, right? The other half of the picture kind of idea. So the idea is look at the whole picture of genetics, transfer the best embryos at optimal endometrial timing, and of course it's only for frozen embryo transfer cycles. That's my last actual slide. I'm going to put up my contact details. If anybody wants to get in touch with me, my business cards are over there. You can certainly come talk to me after. I would be remiss if I didn't introduce my colleague, Casey Cummins, who helped put this all together. Stand up real quick, Case. My field team is amazing, and they do keep me in line. I go all over the place. I give lectures like this all the time, and they're the ones that keep me going in the right direction, saying the right things, doing the right things. And I can't thank Casey enough for coming in the snow to pick me up at the airport. And yeah, thanks a lot for inviting me here in April in the snow. I really appreciate it. It's awesome. And I want to thank Mike and Alyssa for inviting me. It's been fantastic. So anyway, that's our contact details if anybody wants to get a hold of me. If you want the slides, send me an email. I'll send you these slides as long as you promise to keep them to yourself. I can't go to a meeting and see you showing my slides somewhere. I will go on tilt if you do that. But if you need them, if you want to educate people, you want to share them internally, you're going to have them. And you're going to have a video of this on your website for sure. I'm going to take any questions that y'all might have. I'm going to try to remember, you've got the microphone. I'm going to try to remember to repeat the question so that we get a good video of what was said. Because in the end, sometimes the questions are where the best stuff comes out. So thank you all very much for having me. I appreciate it.